Hello, hello, hello. In this worked example, we're going to revisit the Atwood machine, an example which we previously talked about, except now there's going to be a twist. And now, instead of assuming that that the pulley involved in the Atwood machine had no mass, we're going to treat the case of the Atwood machine with a massive pulley, and this will be a good example to use the rotational analog of Newton's second law. So let's dig in. So let me start reminding you about how things went with the Atwood machine. The Atwood machine just consisted of a pair of masses, different masses, connected by a rope. And in the original version of the problem, we specified that the rope had no mass, nor did the pulley. And massless ropes and massless pulleys, of course, exist only in textbooks. And the basic idea was we were going to end up applying Newton's second law to each of these two masses, and we were also going to take advantage of the fact that the whatever the acceleration of one mass was, it was directly linked to the acceleration of the other because there was a fixed length of rope between them. So if mass number two were accelerating downward at a certain rate, mass number one would be forced to have an acceleration of the same magnitude, but in the upward direction. And with that realization, we were able to solve the problem because there really were then two unknowns in the problem. We didn't know the tension in the rope, and we didn't know the magnitude of this acceleration, but we had two equations. We could apply Newton's second law to each of these two masses, two equations in two unknowns. That's a simple algebra problem to solve, and we solved it. So now, again, the twist is going to be we're going to get a little bit more realistic, and we're going to assume no longer that that the pulley is massless. The pulley is now going to have mass. So how does that change things? Well, it turns out that it makes things sort of surprisingly complicated. So before we get to that full-blown problem, let's take a somewhat simpler problem in which there's just a single mass and a massive pulley. So that's the problem I want to consider here. So there's a single block of mass m, little m, and a pulley of mass big M, and let's specify that the pulley has a radius, which we'll call r. And there's also going to be, as in the original Atwood's machine problem, some unknown tension in the rope T that we're going to have to find out, actually, in order to solve the problem. So the basic approach is going to be there are two objects in the system, the block and the pulley. And we're going to apply Newton's second law to the block and get some information from that. And then we're going to apply the rotational analog to Newton's second law to the pulley to get some additional information and put it all together. And let's say that our goal in this problem is to find the angular acceleration of the pulley. So find alpha sub pulley. That's the goal here. So to apply Newton's second law to the block, I'm going to draw a free body diagram for the block. And there's going to be an upward going tension force on the block of magnitude T and a downward gravitational force on the block M times G. So we want to apply Newton's second law applied to this block, applied to mass M. What's that going to tell us? It's going to tell us that T minus mg is equal to ma, where we've adopted the sort of usual sign convention where the acceleration of the block is going to be considered positive if it's accelerating in the upward direction. And now for the pulley, we're going to apply the rotational analog to Newton's second law, which says that the acceleration of the pulley is given by the torque that is exerted on the pulley divided by the rotational inertia of the pulley. Okay, so that means that the acceleration, the angular acceleration of the pulley, the torque on the pulley, what's that? Well, it's by definition, it's the tangential component of the force that's applied to it, which in this case is going to be T, the tension force, the magnitude of the tension force. So T is sort of by definition a positive number here, times the distance between where the force is applied and the axis of rotation, and that is, of course, r, because the force is being applied on the rim of the wheel, and the axis of rotation is here, so that distance is r. Now, there's one complexity here, is that in order to get the signs right, we have to put a minus sign out in front of the torque. And why is that? Well, our convention for defining angular position, it really traces back to that. We defined angular position so that counterclockwise rotations corresponded to increases in angular position. And that means that positive values of the angular acceleration are going to be associated with things that are spinning faster and faster in the counterclockwise direction. And Newton's second law, the rotational analog, means that positive torques are going to be ones that cause the object to rotate in the counterclockwise direction. Negative torques are going to be ones which cause the object to rotate in the clockwise direction. So here, the torque that's being exerted is clearly then a negative torque. And now we've got to divide that by the rotational inertia of the pulley, which we can treat as a disk. And you can look up the rotational inertia of a disk of mass m and radius r is just 1/2 mr squared. So we have this relationship that the angular acceleration of the pulley is equal to minus, and I'm going to put the 2 in the numerator here. Dividing 1 by 1/2 is like multiplying by 2. I have minus 2t over m times r, because one of the factors of r cancels. Okay, well, we're getting closer. So to find out the angular acceleration of the pulley, we need only to know the tension in the rope, because we assume that we're given the mass and the radius going in. And we have an equation down here that for the tension that we can use, except there's one problem. We don't yet know the acceleration of the block. So we're one equation short, but not to worry. There's a simple solution, and that is that the acceleration of the block and the angular acceleration of the pulley are, of course, not independent from one another. They are intimately linked. The linear acceleration of the block is just equal to the angular acceleration of the pulley times r. Right, because the linear acceleration of a point on the rim of the pulley is just the angular acceleration of the pulley times r, and because there's a fixed length of rope between the rim and the mass, it means that the block m, little m, is going to have the same acceleration, linear acceleration, as a point on the rim of the pulley. So that's where this relationship comes from. Okay, so now we're almost there. I can write that the tension in the rope is given by moving mg over to the right is equal to mg plus m times alpha pulley times r. So that's great, because now what I have really are two equations in two unknowns. I don't know alpha pulley going into the problem, and I don't know the tension, but now I've got two equations that involve both of those two variables. So now it is just a simple algebra problem to find alpha pulley. So I will leave it to you to work out the algebra and to show that the angular acceleration of the pulley is given by this expression here. So if we switch to the Atwood's machine, which now there is not only a massive pulley, but two masses, and therefore two unknown tensions, it actually gets algebraically messy pretty quickly. I'm not going to work through the entire problem, but I just want to set it up for you so that you can see how to solve it. So the problem that we'd like to consider here is to calculate the angular acceleration of this pulley. So calculate the angular acceleration of the pulley. Well, because the pulley has mass, it has a rotational inertia, and the governing equation that we're going to make use of is that the angular acceleration of the pulley is given by the net torque on the pulley, which we'll call tau sub pulley, divided by the rotational inertia of the pulley. So in other words, we're going to make use of the rotational analog of Newton's second law. And in order to get a net torque on the torque on the pulley is going to be caused by a combination of torques due to the tension in each of these two strings. One of the strings is going to exert a torque. This one is going to exert a torque tending to cause the pulley to want to rotate in the counterclockwise direction. The torque associated with tension number two here is going to be a torque which tends to cause the pulley to rotate in the clockwise direction. And so we're going to get a net torque, and we're going to divide that net torque by the rotational inertia of the pulley to get the angular acceleration of the pulley. And now, because of the way we've defined the angular position, recall we've defined the angular position so as the pulley rotates in the counterclockwise direction, the angle theta increases. And that ends up meaning that positive angular accelerations are associated with an increasing rate of angular velocity in the counterclockwise direction. So what that means is that we're going to consider torques to be positive as those torques which tend to cause a counterclockwise rotation, and torques which are negative are torques which tend to cause a clockwise rotation. So what that means is that the torque on the pulley in this case is equal to, there's a positive contribution from the torque associated with the tension T1, and that torque is going to be equal to T1 times the radius of the wheel. Because remember, torque is the tangential component of the force times this radial distance to the axis of rotation. So the torque, the force is being applied tangentially. This rope is pulling tangentially on the pulley. So the tangential component of the force is just the tension T1, and it's being applied a distance r from the axis of rotation. So this is the contribution to the net torque on the pulley from this string here. The string on the right, T2, is going to result in a torque with a negative sign in front of it, and the torque associated with this tension force T2 is just going to be minus T2 times R. And the rotational inertia of the pulley, that's something you can look up in a table. A disc, we're going to treat the pulley as a disc. And if the pulley has a mass, which we'll call M, big M, then the rotational inertia of the pulley is just 1/2 mr squared. So putting these last two results into the rotational analog to Newton's second law, that tells us that the angular acceleration of the pulley is just equal to T1r minus T2r divided by 1/2 mr squared. So We have an expression for the angular acceleration of the pulley, but it involves two unknowns. We assume that we're given the mass of the pulley and its radius, but at the beginning we don't know what these tension forces are, T1 and T2. So if we're really going to answer the question that's being asked here, we have to have some way of finding out the value of those tension forces, T1, T2. How are we going to do that? Well, you won't be surprised. It proceeds pretty similar to the way the original Atwood's machine calculation worked. Is we have two different masses here, and that means we have two different opportunities to apply a Newton's second law to those masses, and that is going to help move the calculation along. So let's do that. So for mass number one, I'm going to draw a free body diagram over here. And the forces that act on mass number one are an upward going tension force of magnitude T1 and a downward force of gravity, which is, of course, M1 times G. And similarly, for mass number two, same deal. There's a downward gravitational force, M2 times G, and some upward tension force, T2. And we don't know the magnitudes of these tension forces yet. But there is going to be a net force on each of these masses, and that is going to result in a acceleration. So the acceleration of mass number one is going to be given by T1 plus M1G divided by M1, and the acceleration of mass number two is going to be given by T2, and I'm using vector signs here at this point. So that's Newton's second law applied to each of the masses 1 and 2. And now I want to get rid of the vector symbols. So I'm going to just assume that the upward direction is positive and the downward direction is negative. So I can write A1 is just equal to T1 minus M1G over M1. And I can write A2 is equal to T2 minus MG over M2. And here, T1 is just the magnitude of the tension force 1, and T2 is just the magnitude of the tension force T2. And these are both positive numbers since the tension forces point in the upward direction. Gravity points downward, so I'm introducing a minus sign here. Okay, and now acceleration 1 and acceleration 2 are related to one another. If 1 goes up, 2 goes down, and vice versa. So that must mean that A1 is equal to minus A2. Okay, so I think this is about as far as I want to move the problem along. You can see that we've got a series, it's going to proceed pretty much in spirit to the previous calculation. We have all the enough equations to solve everything, but it is still a little bit of algebra to go, and it gets a little bit messy. So I am not going to bother to grind through this problem anymore. I just wanted to give you a sense of how introducing a simple thing like making the pulley massive needs to be dealt with in problems of this sort. So that is it for this worked example. Hope to see you again soon. Bye-bye.